we already know that a moving charge will generate a magnetic field. But there's more. And what we're going to address in this lesson is a new fact, which is that a moving magnet can generate an electric field. So this sort of helps justify the word electromagnetism, which we've been using recently. Electric and magnetic fields are inextricably linked. An electric charge can create a magnetic field, and a magnet can create an electric field, provided in both of these cases that they are moving. Now here's an example of this concept sort of in action to help paint a bit of a better picture. I have a magnet, north and south poles. And if I move it to the right here, then towards this metal loop or metal ring, then what I will end up having is I will make an electric field formed inside the metal of this ring. And that electric field will push on charges in the ring and cause current to flow around the ring like that. Normally, if I just take a metal loop, I will not get current randomly flowing around it. To get current flowing in a wire like that, I would normally need to cut the wire and put a battery or something in it. But by using a magnet, I can actually generate an electric field without needing to use a battery, and I can push current around a loop that's closed and has no power source in it. So we say that the moving magnet generates an induced electric field inside the metal of the loop. And that electric field will push on the charges in the loop, causing them to move, and they'll create an induced electric current, which is what we're showing here and here. Now, in this diagram, we show current going two different directions in two slightly different scenarios. And so I want to get to a point where we can figure out for ourselves why the current goes this direction in this situation and why it goes this direction in this situation. And to do that, we need to know about something called Lenz's law. And Lenz's law says this. An induced magnetic field acts to undo the change that caused it. An induced magnetic field acts to undo the change that caused it. This is known as Lenz's law. So, let's apply this to our diagram up here. As I take this magnet and I move it to the right towards this loop, there's sort of a change in the magnetic field inside the loop. When the magnet was really far away, say over here, probably not a lot of these magnetic field lines here were actually going through the loop. They kind of bend out pretty quickly, so a lot of them would have missed the loop. But as I move the magnet closer and closer, more and more of these magnetic field lines are going through the loop. So the loop suddenly sees a lot more arrows going to the right. Lenz's law tells us that the loop will then induce a magnetic field that tries to undo this change. So when the loop suddenly sees all these extra right arrows, it wants to fight that. And it'll do that by producing left arrows. So the loop will kind of make its own arrows going this way. So how can the loop do that? Well, if it runs current around itself in this direction here, then we can use our first right-hand rule. So put our thumb in the direction of that current, I, and then loop our fingers around that portion of the loop. And we'll see that our fingers are pointing to the left as they go inside the loop. So let's recap this. The loop, as the magnet moves to the right, the loop suddenly sees an increase in the number of right arrows inside it. It wants to fight that, so it runs current this way, which will create, by the first right-hand rule, a bunch of arrows that are going to the left to counteract these new arrows from the right. Now we can verify this in the other diagram too. If I instead take this magnet and I move it to the left now, I move it back away from the loop, then all of these arrows, all these magnetic field lines that are currently going through the loop will no longer be going through the loop. I'm pulling the magnet away, so I'm pulling those arrows away with it. And then the loop will say, hey, I had all these right arrows and I am now losing them. I want to undo that change. So because I'm losing right arrows, I'm going to try to create more right arrows. And then the loop will run current in this direction. And you can verify with the first right-hand rule, if the loop runs current in that direction, you put your thumb in that direction, you wrap your fingers around the metal of the loop, and your fingers will be pointing to the right. So to make up for the loss of these right arrows as the magnet gets pulled back, this current will create more right arrows, trying to undo the change. That is how Lenz's law works. Now, one thing I want to just continue to emphasize here is that it's very important to understand that the magnet in this situation above must be moving. The loop doesn't simply say, I see right arrows, therefore I'm going to fight them with left arrows. The loop says, I see an increase in the number of right arrows, and I'm going to fight that increase, fight that change with left arrows. The loop is very fine having a magnetic field in it. It's a changing magnetic field that causes this induced current. The magnetic field in the loop must be changing for this behavior to occur. If not, there will be no induced electric field inside the metal and therefore no induced current. Now, in order to better understand how this magnetic field is changing, we need to understand the idea of magnetic flux. And before I give you a definition, I want to just give you sort of a description of how I think about flux that might help you kind of understand what it is. So I want you to think of magnetic flux as the number of magnetic field lines passing through a region. Magnetic flux is the number of magnetic field lines passing through a region. So, for example, up here, if I take my region to be this loop, I can kind of in this diagram count the number of magnetic field lines passing through it. I see I have 1, 2, 3, 4, 5, 6. 6 magnetic field lines are passing through that. So in my mind, I'm kind of thinking that the magnetic flux is 6. Now, we don't actually calculate magnetic flux by counting lines like that. There's a more sophisticated way to actually calculate it. But that's how I sort of think about it, the number of magnetic field lines passing through a region. So if we go back up to this diagram and we kind of think, okay, so how could we change the flux? Well, right now I have 6 lines coming from this magnet here. If I made that magnet a lot weaker, then it probably wouldn't have so many magnetic field lines and I'd have less flux through that region. Or if I made that magnet a lot stronger, then I'd have more magnetic field lines and more flux through that region. Alternatively, if I take this loop and I sort of move it to the right, it'll be over here, where the magnetic field lines aren't so dense, and so fewer of them will go through it. So that tells us that the strength of the magnetic field will affect the flux. If I make a stronger magnet, I'll have more field lines going through my region. Or if I move my region to a new area where the magnetic field is weaker, I'll have less field lines going through it. I'll have less flux. So that's the first thing I want to say that affects magnetic flux is the strength of the magnetic field. Now, the second thing that affects magnetic flux has to do with the loop itself. Let's say I want fewer of my magnetic field lines to go through this loop. Well, I could replace the loop with a much smaller loop. Let's say I replace it with a loop that's sort of this size. Now I would only have 3 magnetic field lines going through there, so I would have less flux. Even though the loop's in the same place and the magnetic field is the same strength, by making the loop smaller, I have less flux. So that's point number 2. The area of the region. In this case, the region being my loop. And there's one last thing that's important that has an effect on magnetic flux. And that's this. Let's say we're looking at this loop. And let's say I wanted you to really quickly make it so the flux through that loop was 0. So no magnetic field lines are going through the loop. But you're not allowed to put the loop in a different location. You're not allowed to change the magnet or put the magnet in a different location. And you're not allowed to make the magnet or the loop sort of bigger or smaller. There is a way to do this. If you take that loop and you rotate it 90 degrees, so instead of sort of facing towards the magnet, the loop, the opening on the loop is sort of facing towards you, right out of the screen, then no magnetic field lines would be able to get through the loop. They'd sort of hit the loop side on, hit the metal, but they wouldn't be able to go through the opening if the opening was rotated so it faced out of the screen. So that third point that matters here is the orientation of the loop, the way the loop is facing. Now let's just jot down a couple key points about that last bit. So if I took this loop and I rotated it so the opening was facing you, facing out of the screen, then the loop itself would sort of be parallel to those magnetic field lines. The magnetic field lines would be flat on the page, and the loop itself would be sort of lying flat on the page. And that's when I would have the least amount of flux. None of the field lines would get through the loop. So let's make a note of this. Magnetic flux is minimized when the region, the loop in our case, is parallel to the magnetic field. Now, how about if I want the magnetic flux instead to be maximized? I want as many magnetic field lines going through this loop as possible. Well, then I don't lie the loop flat on my page. I lift it up and I turn it 90 degrees, kind of the way it originally was in this diagram. So the loop, the metal of the loop is kind of going in and out of the page, and the magnetic field lines are going left, right. In other words, they're at 90 degrees to each other. They're perpendicular. So that would maximize the flux. When the loop is perpendicular to the magnetic field. Okay, so that's how I want you to think about magnetic flux. Think about it as the number of magnetic field lines passing through a region, and it'll depend on these three things. But we're going to actually have to take a formal sort of definition for flux, because we're going to have to calculate it and get a proper number. And that's what we're going to talk about here. So the proper definition of magnetic flux is this. The symbol we use for magnetic flux is the Greek letter phi. It's uppercase. And so, as we said over here, the magnetic flux will depend on the strength of the magnetic field, for which we use the letter B. We also said the magnetic flux would depend on the area of the region. For that, we're going to use the letter A. And we said that the magnetic flux it depends on the orientation, and it'll be maximized when the region is perpendicular to B. So to kind of demonstrate that in our equation, put this little perpendicular symbol there. So to have magnetic flux, to have as much magnetic flux as possible, I need a strong magnetic field, I need a large area, and they need to be perpendicular to each other. Okay. So this is the magnetic flux through a region. This is the magnetic field strength in the region. And this is the area of the region. So this magnetic field strength, as always, is going to be in Teslas. Area is going to be in meters squared. And so the flux has units of Tesla meters squared, or a more common name for it is Webers, for which we use the abbreviation WB, capital W and a big B. Magnetic flux has units of Tesla meters squared or Webers. All right, so now we're ready to calculate the induced electromotive force, or the voltage, that pushes current around the loop in our example. Now, we're used to current moving around an electric circuit when there's a power source, a voltage that kind of pushes it. And indeed, that's what's happening here. We haven't talked about this yet, but when I move this magnet around, it makes a voltage, or an electromotive force. And that acts as a power source that will push current around the loop. And what we're going to look at next is the formula for calculating that. So the electromotive force, abbreviated as EMF, is written with a script E. And I can calculate the induced EMF in that loop with this formula. Negative N times the change in flux over the change in time. And this is known as Faraday's law. Okay, so what this Faraday's law tells us is, if we look back at that loop example, as the magnet moves, the flux through the loop will change. And that'll happen over a period of time. And that will generate an electromotive force, an EMF that sort of causes current to be pushed around the loop. Now this N here is important. N is the number of loops in my ring. Now in this example here, I just kind of have one loop, but as we've seen before in this topic, if I take a strand of wire and I loop it in many loops, I can often magnify the effect I would get. So often a coil like this would actually have many, many loops in it to take this effect and magnify it several times. And that's what this N represents in Faraday's law. It's the number of loops. And we've seen that before in other equations that we've done. Now, one thing I just kind of want to note here, because there's a few words that sort of all mean the same thing. So EMF is short, it's an abbreviation for electromotive force. And electromotive force is sort of an old word for voltage. Voltage is what causes current to flow around a circuit. And people often thought of that as if the voltage was sort of pushing on charges. It was basically a force measured in newtons. Turns out voltage isn't measured in newtons, so it's a little incorrect to call it an electromotive force, but it's one of these terms that we just keep around and we're used to using it. And voltage, remember, from our last unit, is the same as the potential difference. So you'll see all four of these terms used: EMF, electromotive force, voltage, potential difference. All of them mean exactly the same thing. All of these are created whenever there's an electric field. In this case, there's an induced electric field in that ring, and so that gives rise to an electromotive force, or a voltage, or a potential difference. And all of those things are measured in volts. Electromotive force is measured in volts. Voltage is measured in volts. Potential is measured in volts, because they're all exactly the same thing. Now, one other thing in Faraday's law here that I want to address is this negative sign there. That negative sign has to do with Lenz's law. It's basically a reminder that the induced magnetic field will oppose the change that caused it. So if you look back here, remember in this case, our change was as this magnet moved to the right, there were more and more right arrows through my ring. So the induced EMF, the induced current, created a magnetic field that was going to the left, that opposed those right arrows, that opposed that change. That's what this negative sign does here. So this change in flux in the last example would have been to the right, more right arrows. And because I multiply it by a negative number, I'm going to get an EMF that basically is negative, that's to the left, meaning that EMF is going to cause the current to flow in a direction that make arrows going to the left. So that negative sign is from Lenz's law. It reminds us that the induced magnetic field will oppose the change in flux. And that is Lenz's law. So, to recap all of this, when the magnetic field through that loop changes, it gives rise to an induced electric field inside the metal of the loop. And that induced electric field is associated with all of these things. So it's associated with an induced EMF in the loop. And that's what Faraday's law over here tells us. It tells us what that EMF will be. That EMF, which is basically just a voltage, will now cause an induced current to flow in the loop. And when I have a current flowing, that current generates an induced magnetic field in the loop. And that magnetic field opposes the change in the original magnetic field. And that opposing the change comes from Lenz's law. So with these concepts and these formulas, let's now try to tackle a couple of problems. First of all, we're just going to do a problem to do with the idea of magnetic flux, and just see if we can kind of calculate some flux. So, a square loop of wire is perpendicular to a 1.5 Tesla magnetic field. If each side of the wire is 2.1 centimeters, what is the magnetic flux through the loop? So let's see if I can draw this out. I have a square loop of wire. And it's perpendicular to a 1.5 Tesla magnetic field. So let's draw that magnetic field out like this. So I've got a magnetic field going into the page, and it's perpendicular to this region, this sort of loop of wire that's kind of laid flat on the page. The magnetic field is 1.5 Teslas. And the square loop of wire is 2.1 centimeters on each side. So that is 2.1 centimeters, and this is 2.1 centimeters. What is the magnetic flux through the loop? So, if we take this formula for flux up here, can calculate this reasonably easily. Magnetic flux is B times A, and they have to be perpendicular. Well, first of all, let's double check that they're perpendicular. Well, the question told me they were going to be perpendicular, and I can see in my diagram they are too. The magnetic field is going into and out of the page, while the loop itself is sort of laid flat on the page, parallel to the page. So, because they're perpendicular, all I have to do is take that magnetic field and multiply it by the area of the region, in this case, the loop. So the magnetic field has a strength of 1.5, and the area of the loop, well, that's going to be length times width, or because it's a square, just the length squared, and length is 0.021 meters, and I'll square that to get the area. So that gives me a flux of 6.62 times 10 to the negative 4. And the units will be Tesla meters squared or Webers. Okay, so that's just a simple calculation of flux. Let's now kind of apply it to an example. So here we have a circular loop of wire, kind of like that ring we started our lesson with. We know its radius and it's placed in a magnetic field that's going into the page. Then that magnetic field is reduced to a smaller value over a period of time. And we want to know the EMF. So this is going to play exactly into Faraday's law up here. We have a magnetic field being reduced, so the flux is going to change. They told us about a period of time, and we're trying to find the EMF. So I'm going to write down that formula because I think that is going to be important. Here's Faraday's law. And let's draw this out. So I have a circular loop of wire, and it's in a magnetic field. And that magnetic field is reduced. So I've kind of got my initial situation over here, where my magnetic field is 0.2 Teslas. But then I've got a final situation, which I'll draw over beside it, where the magnetic field is now only 0.01 Teslas. So let's redraw my loop over here. And my magnetic field will now be reduced. Okay. So, in this situation, we're going to try and apply Faraday's law. So, we need to know the number of loops. Well, I just have one loop, a circular loop. This is not a wire that's been coiled around many, many times for many, many turns, and is just going to be one in this scenario. So that part's fairly straightforward. I will need to know, however, the change in flux. So what I'm going to do here to find the change in flux is this. I'm going to say the change in flux is flux final minus flux initial. That makes sense. The change in anything is final minus initial. So flux final, well, flux is B times A. So that'll be B final times A final minus B initial times A initial. But when you look at this question, A is not changing. A final and A initial aren't any different. A is the area of the loop. I have the exact same loop here as I do over here. The loop does not change. It's the magnetic field that changes. So I don't have to write this as A final and A initial. I can just write it as A, and then I can even factor it out to clean things up a bit. Now for B final and B initial, final is 0.01, initial is 0.02. And what I can do is I can kind of assign those a direction if I want. I, however, prefer to just use this equation, just use Faraday's law with positive numbers, just with magnitudes. There's no real vectors in here. A negative doesn't really mean the same thing for a change in flux as it does for a voltage or an EMF. So I just avoid any negatives whatsoever when I'm using this formula. I only use it with magnitudes. And this negative here, I just think of that as a reminder about Lenz's law. That when I go to find the direction of the current, it's going to act in a way to oppose the change in flux. So, with that in mind, my area, well, this loop is a circle, so area is going to be pi r squared. So pi, and the radius it said was 2.5 centimeters. So pi times 0.025 squared. And then B final was 0.01. And B initial was 0.02. So that gives me a flux or a change in flux of 1.963 times 10 to the negative 5. And that'll be Webers. But my goal here is not to find the change in flux. My goal here is to find the induced EMF, which I can do up here. So now that I know my change in fluxes, I can go back to that original equation. And I can say the induced EMF is negative N times the change in flux over the change in time. And again, I'm just ignoring all negative signs here because we don't really have any vectors, and negative kind of means a different thing for flux than it does for EMF. So we're just working with magnitudes. You might notice that this here would give me a negative number. Didn't even throw that negative in. I'm just working with magnitudes. So let's ignore that negative. It's just a reminder to use Lenz's law later. N, the number of loops, is just going to be 1, so I don't even have to write it. So all I have to write down is my change in flux, 1.963 times 10 to the negative 5. divided by my change in time. How long does it take for that flux to make that change? That was given to us in the problem. It's 0.1 seconds. So that gives me an EMF of 1.96 times 10 to the negative 4 volts. So let's pause and reflect for a second. I had a loop of wire. Normally, current shouldn't flow in a loop of wire unless there's a power source, like a battery. But in lieu of a battery, I had a magnetic field. Now, just the magnetic field by itself didn't cause any current either. But when I took the magnetic field and I changed it, then I was able to calculate a number in volts. I was able to calculate a voltage. This loop, even though it's not connected to a battery, it has a voltage in it. And that voltage is going to drive current and start making current flow around the loop. This is kind of the magic of electromagnetic induction. I can kind of create a power source without a visible battery or anything like that. Sort of invisibly, just by having a magnetic field nearby that's changing. Now, note that this voltage is not very high. It's easy to get a voltage from like 1 to 10 volts on like a regular consumer battery you buy at the grocery store. This voltage is much less than that, but we could make the voltage bigger with a stronger magnetic field. These don't look like very strong magnets. We can make it bigger with a bigger loop, and we can make it bigger by having that loop have multiple turns in it. So pretty quickly, if we make some changes, we can get a decent-sized voltage out of this. Now, the last question we have to answer is which direction does the current flow? So we know we have a voltage in this loop. It's going to push current. Is it going to go clockwise or counterclockwise? Well, that's where this negative is going to come in, which you'll recall is a reminder about Lenz's law. And Lenz's law says that the induced magnetic field, the magnetic field caused by this current we're going to get in the loop, will act to undo the change that caused it. So, if I'm this loop, let's look at the change I had. Over here, I had a lot of X's. And now I have less X's. So I lost X's. And I'm going to try to fight that change. If I just lost some X's and I want to oppose that change, I'm going to create more X's. So, which way am I going to run current in this loop in order to create more X's? Well, the right-hand rule will show you that if you run current in this direction, that will create a magnetic field, which gives me X's outside the loop and dots inside the loop. Well, that's the opposite of what I want. Often with these things, you got to kind of have to guess and check. So if I run current in this direction, that would create a magnetic field that gives me X's over here inside the loop and dots over here outside the loop. It's the inside of the loop that I always care about. That's where I'm interested in the change in flux. So a current going in that direction will create extra X's inside the loop, which helps make up for the fact that I lost so many X's when I went from this magnetic field to this magnetic field. So the current will flow clockwise. To create X's in the loop, to make up for the X's that were lost. Now, before I close this lesson, I want to kind of bring us back to real life for a second. There's something pretty substantial that we've just learned. We've just learned that a moving magnet, resulting in a changing magnetic field, can create an electric field, which will cause current to be pushed and give me electricity. I can make electricity by moving a magnet around. That is not only kind of nifty, but it's hugely useful. In fact, that's the way that most of the electricity we use is produced, by moving a magnet. Let me kind of walk you through that. So when I think of the common ways that electricity is produced, here's what I think of. Wind turbines is one of them. Wind goes past this turbine and it spins those blades in a circle. Well, guess what's inside that pillar on the back of the blades? Some magnets and some coils. And as those turbines spin, the magnets and the coils will move, and that will induce some electric current. It'll make electricity. How else do we produce power? Well, here's a hydroelectric dam. Got a big lake or reservoir being held back by a big dam, and when I choose to, there's some big pipes underground I can let that water run through. If I look at a diagram, it looks kind of like this. I can let the water on the left run through that big pipe called the penstock, and as it does, it'll run past some blades in a turbine, and it'll cause that turbine to spin. Basically, this is a glorified water wheel. So now I have something spinning. Well, what's hooked up to that spinning thing? Some magnets or some coils. And then when I have those magnets and those coils moving relative to each other, I'll get an induced electric current and I'll make electricity, which hooks up to these power lines and heads out to the grid. How else do we make electricity? Well, there's the option of kind of like burning stuff to heat water. And so this, what we're looking at here, could be a coal power plant that burns coal to make heat, or it could be a natural gas power plant that burns natural gas to make heat, or it could be a nuclear power plant that runs a nuclear reaction to create a ton of heat. Any of these three, whether we're burning coal or natural gas or running a nuclear reaction, we're creating heat. And what do we do with that heat? Well, we run some water by that heat in some form of boiler. And what does that water then do? It'll evaporate, it turns into steam. That steam runs through some pipes, and then that steam will rush past, yes, a turbine. Just like the water over here was rushing past a turbine, the steam we've created over here is rushing past a turbine, and it'll spin that turbine in circles. And what's hooked up to that turbine? Some magnets or some coils. And when those magnets and those coils move relative to each other, they'll induce an electric current and I get electricity. So wind power, coal power, natural gas power, nuclear power, hydropower, all of these basically work the same way. We get something to spin a magnet or a coil, and that changing magnetic field induces a current, makes electricity. Now, the one sort of common example of power generation that we do that does not use this principle, does not use electromagnetic induction, is solar cells. These work on a totally different physics concept and doesn't require any moving parts. But as of the time of this video, solar panels make up a pretty small percentage of humanity's electricity production. But they're notable in that they're kind of the one example that does not use electromagnetic induction.